Methods of thermal energy transfer. There are three methods of thermal energy transfer: conduction, convection, and radiation. The definition of conduction is transfer of thermal energy through atomic vibrations. Basically, as particles in solids are vibrating, they collide with each other. During those collisions, energy is transferred from the faster moving particles to slower moving particles. This allows transfer of heat energy across the medium. Convection is transfer of thermal energy through movement of particles in fluids. And radiation is transfer of thermal energy through electromagnetic waves. Let's start with conduction. Conduction is transfer of energy through a solid with atomic vibrations and energy transfer between particles as they vibrate and collide. So in this simulation, you see the heat energy transferred from right to left as each particle collides with the next one. Conduction is an important factor in many engineering projects. To quantify the amount of energy conducted through different materials, the term thermal conductivity is used, whose symbol is K in this formula that is given in the data booklet in section B1. It is defined as how good a thermal conductor is at transferring energy through itself when it is in steady state. So this diagram shows the explanation of this formula over here. The rate of energy transfer through a material, which is given as delta Q over delta T, is equal to the product of the thermal conductivity times the area of the material times the value of the temperature change across a certain distance x. This formula helps us calculate the rate at which thermal energy is transferred across a certain displacement and the change in temperature that occurs within that displacement. Next is convection. Imagine a fluid, this could be gas or a liquid, fire in the middle of a room. The particles near the fire will gain the heat energy and move faster. This decreases the density of the air in that area, which causes those particles to spread and rise. The space that is emptied by those particles is filled with the colder air particles, which are vibrating more slowly. So this causes a flow of heat energy throughout the liquid. This is called convection. So here I was making iced tea. You can see the flow throughout the liquid, which actually moves the lemon with it. Convection is also how you feel the heat when you place your hand right above this fire. Now, not all heat is transferred through movement of particles. How do we get heat energy from the sun? For that to happen, heat energy must be able to reach us moving through vacuum, which is empty space, in the form of electromagnetic waves. So the infrared section of the electromagnetic spectrum is responsible for the transfer of heat energy. So that is called heat transfer by radiation. When you hold your hand next to the fire, you still feel the heat energy, and that is radiation right there. All right, moving on to a new definition. A black body is the name given to any object that is able to absorb and emit all radiation. Stars are said to be black bodies, so they can absorb and emit the whole electromagnetic spectrum. And that doesn't mean the object appears black, but it is a description of what an object can absorb and can emit. If an object completely absorbs and emits all radiation, that is called a black body. These graphs give us the relationship between surface temperature and the peak wavelength emitted by black bodies. So black bodies emit all wavelengths, but there's a peak wavelength which determines the color that it is observed for us. For example, if I increase the temperature on this curve, you see that the peak wavelength of the curve shifts to the left. And as temperature decreases, the peak wavelength shifts to the right, which gives us the inverse proportionality between surface temperature and the peak wavelength emitted by a black body. To mathematically relate surface temperature and the peak wavelength emitted by a black body, we use these graphs. Your data booklet, you will have this formula right here, which is called Wien's law, relating peak wavelength and surface temperature in Kelvin. So you can see that they are inversely proportional and their product equals to that constant. This is given in your data booklet. If you have a graph like this, you can see, for example, for this curve, the peak wavelength corresponds to 1000 nanometers. If you substitute 1000 nanometers here, you can calculate the surface temperature in Kelvin. And you can see as the wavelength gets smaller, the temperature gets higher and the intensity also gets higher. A blue appearing black body is much hotter than a red black body. So here's an example. The sun has an approximate black body spectrum and most of its energy is radiated at a wavelength of 500 nanometers. To find the surface temperature, you can substitute that wavelength value into Wien's law, which is going to give you 5800 Kelvin, which falls in the yellow region, Stefan-Boltzmann law. The sigma in this formula is the Stefan-Boltzmann constant, which is given as such. It is also given in the table of constants in your data booklet. The term that I need to explain here is E, which stands for emissivity. So emissivity is the ratio of the power emitted by a surface to the power emitted by a black body of the same dimensions at the same temperature. So emissivity is the ratio of how much power it emits to how much power it would emit if it were a black body of the same dimensions and the same temperature. Since black bodies are perfect emitters, E for a black body would be 1. In this formula, P is the power emitted by any object, E is emissivity, sigma is the constant, A stands for surface area. Please remember that for spherical objects, surface area is calculated by 4 pi r squared, and T is the surface temperature in Kelvin. It's very important that you remember that T in this formula must be in Kelvin and not in Celsius. Stefan-Boltzmann law helps us understand how we gather information about stars. Luminosity represents the power radiated by the star, and its apparent brightness is the power received per unit area. In other words, the intensity. The relationship between L and B are given in the data booklet, and it is an application of the Stefan-Boltzmann law. This relationship is an example of the inverse square law, which we encountered while discussing fields when we learned about the gravitational and electric forces. Here's a summary of the two terms luminosity and apparent brightness. It is important to note that the symbol shown here represents that of the sun for any term that it is placed next to. So how do we use these to get information about stars? The observed color suggests the peak wavelength, which gives us its surface temperature. We can measure its apparent brightness and determine its distance using various methods which are outside the scope of our curriculum. Using Stefan-Boltzmann law, we can calculate its luminosity, and this lets us calculate its radius.